Okay, we are talking about aldehydes and ketones. And remember that each of these have some functional groups. So the functional group there of our aldehyde is this guy right here. Remember that because of the hydrogen, this functional group will always be at one end of the molecule or the other. So hydrogen doesn't have too many bonds. We also have our ketone, which is always sort of a 3-carbon run together, where the central carbon has that double bonded oxygen, and that is our ketone. The carbon oxygen double bond is what's known as a carbonyl group or carbonyl carbon. And that is, as we talked about, a polar sort of bond there, if you will. Again, the carbon being more positive, the oxygen being more negative. Now, in terms of naming aldehydes, we basically will just kind of drop the last part and we will replace it with an Al. So again, we had something like this. We are still looking for the longest carbons, which in this case is 2. It has the functional group part of it. And again, that's going to be based off of ethane. And that would then be ethanal, Al at the end. Remember as well, because this functional group has to be at the end, you do not need to give the location where the carbon-oxygen double bond is. But as we saw in a number of examples, if there are other groups attached, numbering wise, that carbon-oxygen double bond there should always be carbon number 1 in terms of how to number any other groups that are attached. Groups attached like normal, alphabetical order, numbers, all that good stuff. Ketones a little bit different in terms of ketones. We'll do something like this. Here, once again, we could see our ketone group right there, 3 carbons in a row with our carbon-oxygen double bond happening right there. So again, we're going to count the carbons involved with that. And in this case, it's all of them. And that is 5 carbons, which is based off of pentane. We do drop the last part and actually put ONE, kind of like ketones, ONE. And in this case, though, this is about where with ketones that you do need to give the location of the carbon-oxygen double bond. This is about where you could have more than one option. And in this case, no matter which way you number, this is going to be number 3. Again, if you started in this direction, it's going to hit number 3. So this would be 3-pentanone in this particular case. Again, when you do need to give the number for the carbon-oxygen double bond in a ketone, it needs to be given the smallest number is kind of the preference there. Once you lock in your numbering for your carbonyl group there, anybody else that's attached is numbered the same way accordingly based off of that. Questions on any of that there? Now, because they also have the carbonyl group, right, it does make aldehydes and ketones relatively soluble in water, smaller ones, less than 5 carbons, again, because water can hydrogen bond between the hydrogen, for example, and the oxygen in this case, and it will make it soluble. Again, solubility will start to decrease as we talked about as soon as you hit that kind of magic 5 number, which is for most things in organic chemistry. You get up to about 5 or more carbons. Solubility, again, with water will start to decrease. Ketones and such cannot hydrogen bond with itself because it's missing a proper hydrogen to do that, but water can supply the hydrogen to hydrogen bond with in this particular case. Any questions on that there? All right, so I don't think we did this one right. I don't think so. So why don't we do this one? Why not? Let's identify them as an aldehyde and ketone, and why don't we also name it for good measure? So why don't you give the names and identify them? Okay, so let's take a look. We'll start the first one here. So hopefully you can see it. We have a 3-carbon run right about there. And in the middle of that 3-carbon run is our double bonded carbon to the oxygen. That should tell us this is a ketone, right? And in this case, we're going to count the carbons. We got 1, 2, 3, and 4 carbons. That's going to be based off of butane. We're going to drop the last part of the name there and go butanone, O-N-E, in this particular case. Here, we actually don't need the numbering as we talked about because it's pretty much 2 no matter which side you put it on, it'll be the same number. So again, that's basically about 5 or more is where we need to start kind of giving that number here. Any questions on that one? Here is hopefully the functional group you recognize. That is our aldehyde group there, found at the end, which is good. And this is 1 and 2 carbons, like the one I just did there. And that's going to be ethanal here, Al at the end of it. Again, no need to give the location because it should always be at the end. Here again on the C, we see the aldehyde group at the very end. Counting this up, we got 1, 2, 3, 4. And to be truthfully honest, you could also get 4 by going this way, or you could get 4 by going up. It doesn't really matter which way you want to choose. Again, since we got a few options to get to 4, I'm going to go with maybe the straightest option there. So if I kind of box around this here, that is 4, which means it's going to be butanal, Al. We do not need to give the location, but for our purposes here, that is definitely going to be carbon number 1. Number 2 and number 3 is important because we got a couple of methyl groups hanging out there. That is 2 methyl groups in the same compound. So that is a dimethyl. I'll go up higher. Dimethyl. And we do have butanal, and we do need to give the location, right, of where those methyls are. And they both happen to be on the same carbon. So remember, even though they're on the same carbon, you do still need to give the number twice. So this is going to be a 3, 3 dimethyl butanal. Any questions on that one there? And lastly here, carbon, carbon, carbon. With the double bonded oxygen there in the middle. So right there is our ketone group. And this is obviously a cycloalkane base ring, and that is a 6-member ring. If we just fill it in there, that is 6 right there. So that's going to give us cyclohexanone in this case, O-N-E. Again, no need for the numbering of it in a ring structure like this. Again, though, it would be carbon number 1 if you had something else attached to the ring, right? And that's how you would number. Any questions on the identification or names? Okay. All right. Okay, so let's take a look. Obviously, these are ketones because they told us, but just in case they didn't tell us, here again is our ketone group on this one right there. And obviously on the bottom one right there is our ketone group, our 3 carbons in a row with the oxygen double bonded there. So we'll start with the first one. Let's just count. We got 1, 2, 3, 4, 5, 6 carbons. So that is going to be hexanone. Here we do need to give the location of the double bonded oxygen, and that's going to be at carbon number 2, would give us the smallest number. So a little 2-hexanone there. Coming here to the bottom, obviously it's a ketone. We want to count the carbons. That is 1, that is 2, that is 3, and that is 4. That is a chlorine, not a carbon, even though it has a C in it, right? So 4 is going to give us butanone. Don't need the location of this guy, but that is going to be our lower number, obviously, in terms of numbering. And in this case, 2, 3, and 4. So that is a 4-chloral butanone. Yeah. Any questions on that one there? All right. All right, we talked about some of these reactions already, so we're not going to go and go through them again, but we talked about dehydrating our alcohol. Again, remember on the dehydration of alcohol, we basically take out water and put the double bond back in. Oxidation reduction, we talked about obviously a number of times. So primary alcohol, hydrogen goes out, double bond goes in. Secondary, or we could actually oxidize this one more time. Remember, when we do take the aldehyde, we could oxidize it by putting in oxygen in here, and that will give us a carboxylic acid. And you can take the aldehyde to one more step there and oxidize it to a carboxylic acid. And again, we're just basically inserting an oxygen in that location. It's way more complicated than that, but an oxygen ends up right at that location when it's all said and done to make that carboxylic acid. And that is also another definition of oxidation, right? Is adding oxygen as you go from reactants to products, just like losing hydrogen is a definition of oxidation. Secondary, again, hydrogen go off, double bond goes in. That makes our ketones. Ketones will not continue to oxidize. And here we cannot oxidize, obviously, as we talked about, a tertiary alcohol, as again, we're missing that second hydrogen that is necessary. All right, this we kind of went through. We also talked about our thiol reaction, right? Making our disulfide bond. And basically it's an oxidation reaction because we are taking out H2 and we're going to get that disulfide bond bridge. We also talked about the reverse reaction, which is going in this direction, where you basically add the hydrogen back in and it breaks it back apart. And everybody gets a hydrogen back, a one on each side, and you go back to your original one. So oxidation, putting it together, reduction would be, again, breaking it back apart by putting the hydrogen back in between the two sulfurs. Now, there are a couple of tests that you could use to kind of determine whether or not you have an aldehyde, say, versus a ketone. And one such test is what is referred to as the tolerance test. The tolerance test actually uses silver, and silver actually gets reduced to solid silver, and it makes obviously what is sometimes looks like a mirror sort of reflection in the test tube. And in the process, our aldehyde here gets oxidized. Again, the oxygen is going to come in. So our aldehyde gets oxidized to our carboxylic acid. In the process, our silver gets reduced, and this would be a positive test for the presence of a aldehyde. This would not work for a ketone because it will not oxidize to a carboxylic acid. So again, if you were not sure between the two and you put it in there and you saw a positive test, and you probably had a aldehyde to start with. If you got a negative test and those were your two options, then perhaps you had a ketone to start with. Another similar test is the Benedict's test, and the Benedict's reagent is blue there, copper 2. Same idea here. The aldehyde is going to get oxidized, so we're going to throw an oxygen in there to make our carboxylic acid. In the process, our copper is going to get reduced from copper 2 to copper 1, actually. And the copper 1 is more of a, I don't know, depending on your reaction, orangey, reddish, gross looking type color that maybe you've seen. And the copper is obviously more of a blue color to start with. So again, same result, just a different reagent that's used. And if you use the Benedict's reagent and you see it kind of turn to this reddish sort of color from blue, it would be positive that you have an aldehyde, and probably negative if you obviously had a negative test and you were testing maybe a ketone. You would get a negative one in that case. And this is what it sort of looks like, although in my experience, it's sometimes a little bit more orangey, grossy looking, but kind of this reddish color that occurs. Any questions on that there? So those are two tests that you could use to kind of test for the presence of an aldehyde. And it's based on basically the aldehyde being able to be oxidized to a carboxylic acid, while the ketone will not be oxidized, and again would give you negative tests for both of these. Let's talk about the reductions of aldehydes and ketones using H2. And the reduction reaction is really the opposite of the oxidation reactions we talked about with alcohol. So remember that to make our aldehyde, for example, we actually start with, again, a primary alcohol. And again, we're going to oxidize it by removing our two hydrogens. Hydrogen comes off, and as we talked about, nothing else changes here, except obviously we need to fix it at the end. And the way we fix it is we do need to insert our double bond, which will make, again, our aldehyde in this case. Now, the reduction reaction is actually the reverse reaction. So if you started with the aldehyde here, so let's just say we started with the same aldehyde. And we're going to add H2 to it, which again is essentially H and H. And really this reaction is pretty much identical to the alkene reaction where we talked about the hydrogenation, where we had the double bond. The only difference really between what we saw in the alkene case and this case is when we were talking about the alkene, we actually started with a carbon-carbon double bond, right? And we added our hydrogen. And here what we did is we had to make that carbon-carbon double bond into a single bond, right? To give a place for each of those hydrogens basically to add on. So the only real main difference here is it still happens at the double bond, except that that is your double bond basically, yeah? So when you want to do this reaction here, and you're going to do basically a reduction of an aldehyde, you're going to basically follow the exact same playbook here that we did here, which is you're going to copy it exactly the same, except I need to make room for those hydrogens to come in. A reminder that in organic chemistry, it is not often put in there, but there are electrons there, right? So at this point, everybody has 8 electrons and it's full. So this is why we need to actually make it into a single bond to make room for it. So you would do the exact same thing, just going to draw it exactly the same way. The only difference is we're just going to turn that double bond into a single bond. The exact same thing that we do in the alkene situation. And just like in the alkene situation, we do not put the hydrogens on the same carbons, right? So same idea here. The hydrogens goes to the carbon and the other one goes to the oxygen. So where that double bond was, we put a hydrogen and we put a hydrogen, and we get back our primary alcohol in that particular case. Question on that one there. Now, this is the same sort of thing that happens with a ketone as well. So you could do this with a ketone. And if we look at our ketone, again, a reminder of how we got our ketone in the first place. So to get our ketone and make our ketone, we're going to take a secondary alcohol. Again, we're going to oxidize it, which means we're going to get rid of this hydrogen and this hydrogen, which will give us our H2. Once again, we're just going to draw it exactly the way it is. And in this case, since we remove the hydrogens, we will then have to insert our double bond in there to make our ketone. Yeah. So very similar to the one we just talked about, if you wanted to do really the opposite sort of reaction, which is the reduction reaction, and you started with this ketone, and you want to reduce it by adding hydrogen, which again is just 2 hydrogens. Once again, the important part is right there where the double bond is. So all you're going to do, again, is copy what you got there. we're going to make our adjustments so we now have room for the guys coming in. So we're gonna get rid of a bond. And now, just like we did on the previous one, we're going to add a hydrogen once again to two locations, to the oxygen and to the carbon in this case. This again gives us back our secondary alcohol. So the reduction of ketones are aldehydes. Remember, when we have these guys, this right here is really the important part. And all we have to remember is, again, like what we do with our alkenes, we're going to make some room for what's coming in, and really on this guy as well. All right, that's what we're going to do. So once again, we could copy, as we've been talking about, pretty much the beginning guy, and you'll have, 97% of the answer drawn for you. So that's what we're going to do here, is just kind of copy what's given to us, because we don't want to overlook friendly things that are given. All right. Again, we need to make our appropriate adjustment, which in this case is going to turn it into a single bond to make room for what is coming in. We will still have the hydrogen there at the end. Now that we made room for those two hydrogens that are going to come in, once again, as we talked about, I'll just draw them out. One hydrogen there and one hydrogen there. Once again, we go from our aldehyde to our primary alcohol in this case, right? Any questions on that one there? Here on the bottom, pretty much, rinse and repeat on it. So we're going to basically copy the whole thing again. In this case, it's more condensed like formula. And again, I'm not really concerned about anything other than now making room for it. And that will go here. And now we could put our hydrogens in where we made room. And once again, in this case, I'm just gonna, like I said, draw it out here so we could see them coming in. And in this case, we end up with our secondary alcohol from our ketone that we started with. Yeah. Any questions on that one there? All right, so these reactions here that we just talked about obviously are basically the reverse of the oxidation of our alcohols. So that's how we make them. And then we want to kind of get rid of them and make the alcohols back. This is the reduction part of it, which basically will do the opposite. Any questions? All right. All right, so once you select which product you think about what you're starting with, right? So what I'm starting with in this case is what? This is a alcohol, right? And it is a secondary alcohol, right? This guy is attached to two others, actually carbon, when we get there, two other carbons. And this helps you perhaps if you understand the reactions and what you get, because now I know really if I have a secondary alcohol and I oxidize it, what organic do I end up with? I end up with a ketone, right? Just like if I oxidized a primary alcohol, I will end up with an aldehyde if I do it once, right? A carboxylic acid if I continue to oxidize it. So really, I don't need to draw anything because the only one that's a ketone is that one right there. Now, if you want to just draw out like we've been doing, you should know this is an alcohol. We're going to get rid of the oxygen there, hydrogen there, going to get rid of the hydrogen there, and nothing else is going to change except now we need to put our double bond in there to make our ketone. And looky, that should match. Yeah. So we end up there. So you could do it either way, but sometimes it's good to just kind of look at it. And a reminder up on Canvas, there is a reaction sheet I sort of made. It kind of tells you how to do everything and what you get when you do that. You might just want to look at that if you haven't looked at it already. I try to just in words tell you what happens in the simplest way to get you to your products. But so again, sometimes it can save you some time if you kind of just know secondary alcohol oxidized to a ketone. Clearly, in this case, there's only one choice of ketones, and that will get you through it quicker. Any questions on that there? All right, so let's try this one here. We're looking for really bad lettering here. I think B wants to go here, and maybe C over here, yeah? So what do we get for each of those there? All right, so what should we get after the first? Okay, so let's kind of take the same approach. We'll start with what we got. We clearly have an alcohol. That's the carbon that has the OH attached to it. It's attached to one other alcohol, one other carbon, which means It is a primary alcohol. So what I do know is if I oxidize a primary alcohol, I should end up with a aldehyde. Yeah. And looking at my choices, this seems to be the only aldehyde that is present. And again, that is because we're going to oxidize this guy, right? We're going to take away that hydrogen, and basically double bond where we did that. And we're going to end up with that, right? Now, if I take this guy and oxidize it again, I go from an aldehyde to a carboxylic acid. The second oxidation is where the oxygen just gets inserted basically there, and everything else stays the same. And by the way, if you knew it was a carboxylic acid, that's the only carboxylic acid present as well. So you could quickly identify what you get without maybe having to draw it if you understand the functional groups and you understand what you get as a result of those reactions. Any questions on that there? All right, so why don't you draw the product you get when 2-propanol goes through an oxidation and also a dehydration. Dehydration, right, means taking out water, right? So let's see what you get there. 3 carbons, and the 2 tells us that is where our OH is going to be, right? So we could fill in our hydrogens in this case. I'll actually draw the hydrogen out on that particular one. And first off, we're going to oxidize it, which means this is a 1,2 secondary alcohol, right? As this guy is connected to 2 carbons. And again, I should already know when I oxidize a secondary alcohol, I should end up with a ketone, as we just talked about, right? And again, this is going to come from removing our 2 hydrogens like we've done previously. And nothing else is going to change, except obviously we need to kind of fix it up a little bit by putting in our double bond really to make our ketone in this case. And we get the simplest ketone you could get, which is propanone, right? In this case, question on that one there. All right, then let's dehydrate this guy. In this case, I'm going to actually draw out all the hydrogens just so we can see everything a little bit better. So again, if we started with our 2-propanone, dehydration, right, usually involves some heat, right? And in this case, it means we're going to actually remove water. So as we talked about, clearly the main component of water in this case is definitely the OH is going, right? And when we get the other hydrogen from, it is from not the same carbon, right? But it needs to be a neighboring carbon. And if we did have a choice of different hydrogens on those carbons, we need to pick the one with the least number of hydrogens, right? But in this case, if we go to the left, that carbon on the left has 3 hydrogens attached to it. If we go to the carbon on the right, it has 3 hydrogens. So in this case, it really doesn't matter which hydrogen you grab. I'm going to grab the one over here to the right. And again, you could have grabbed any of those hydrogens on the right. And by the way, again, like I said, in this case, it doesn't matter. You could have grabbed any of the hydrogens on the left as well. So that is where our water is going to come from, right? So 2 H's and an O is going to make water. Once again, as we talked about with this, we shouldn't get fancy with it either. We should now just draw everything that's still there. Obviously, we should take the water out, right? And because we took the water out, we're now short a bond. We need to insert our bond and get our alkene in this case. So again, if you dehydrate an alcohol, you get an alkene. And that is the reverse reaction of if you put water onto an alkene, you get an alcohol, right? So this is like the reverse of putting the water on. Question on that one there. Yeah. So if there is a difference, and in this particular case, there is not. So when we're looking at these carbons here, in this case, they both have 3, so there's no difference. But if there was a difference, you would actually take it from the one with the least. And that's opposite of how the hydrogen goes on, right? When we put the hydrogen on, like when we put water on or HBr or something like that, the hydrogen will end up at the carbon with the most. So when you put it on to the most, when you take it off and dehydrate it, if there is an option, you take it from the one with the least. Other questions? All right. We're not going to draw this, but let's just talk this one through. So this is a Tollens reagent, right? Which means we're looking for an oxidation to a carboxylic acid to occur, right? And that would give us a positive test. Should A give us a positive or negative test? What type of molecule is A? It is a aldehyde, yeah, because it ends in Al. So when I oxidize an aldehyde, that is going through the second oxidation from the alcohol, we will get a carboxylic acid, right? And again, that is the one where we will insert the oxygen there, basically. I didn't draw the rest of the molecule, obviously, but that's the functional part of it. So this should give us a positive test, and we really should just end up with the same guy, just as a carboxylic acid, same number of carbons. In this case, it would have 4 carbons basically attached. How about this one? Should this give me a positive test? Ethanal, Al. Yes, the same deal. This is also an aldehyde. This is one we drew already. That is this guy. This getting oxidized will basically be this guy, exactly the same, except just going to insert an oxygen to make my carboxylic acid group there. And that also should give me a positive test. How about butanone? That is a ketone, right? And that is this guy, basically functional group. This will not get oxidized, yeah? And it will not go through oxidation to a carboxylic acid. So this should be a negative test, yeah, in this case, yeah? So you want to get an actual product in this case. Any questions on that one there? All right. 2 more reactions to finish out this chapter that I want to talk about, which is a couple reactions that aldehydes and ketones undergo. So we're going to start with our aldehyde. I'm just going to make a nice simple aldehyde, I think. Actually, we'll steal the one we just looked at. So we're going to steal ethanal here, which is our aldehyde. And if you take an aldehyde and you actually add a alcohol to it, they will actually react. And the way they react is this way. The alcohol will basically add on, in this case, and it's going to add on as like a 2-parter, if you will. It's going to be this oxygen carbon group, and the second part of it will be basically a hydrogen. So basically, this is going to add as H plus and negative, in this case, oxygen with 1 carbon. Now, if you had to take a wild guess as to where they're going to go, where would you think they're going to end up on that aldehyde? Where has everything pretty much ended up on that aldehyde? They've all ended up here, yeah? So again, this is where they're going to go. Now, that is our carbonyl group, right? And we talked about at the beginning, it is a polar group, right? Which means the oxygen is more negative and the carbon is more positive. So now if you had to double guess, where do you think the positive hydrogen is going to end up? Opposite attracts, right? So that positive hydrogen is going to end up over at the negative oxygen, and the negative oxygen carbon group is going to end up at the carbon, yeah? And that's where these 2 guys are going to end up. Can I just put them on the way it is? No, just like we couldn't put the 2 hydrogens on, right? What do we have to do before we put the 2 hydrogens on? Make that double bond into a single bond. Same thing happens here. So we're going to basically have the exact same thing. And all we're going to do now is make a little bit of room for everybody that wants to come in for some reason here. And I'm going to draw those guys coming in a different color here So again, our positive guy is going to be attracted to the opposite charge, and really our negative guy is going to be attracted to the opposite charge. This is going to give you this guy right here where the hydrogen comes in, and I call this like an oxygen carbon type group on the bottom. And this has sort of a special name. This is what is known as a hemiacetal. So what makes up a hemiacetal? There are a few parts to it. A hemiacetal has an OH group, like we have here. It has an oxygen carbon group, like we have here, that comes from the alcohol. And it also has a hydrogen, like we got here. So those three things is what you're looking for. All attached to that carbon right there are a carbon, and that is what is known as a hemiacetal. Any questions on that there? Now, this hemiacetal can actually react further by reacting with a second alcohol. And it could be the same alcohol or it could be a different alcohol. We'll just use the same alcohol here. So if we threw a second alcohol onto it, it is going to basically do a similar type of situation. And the similar type of situation is this. It's still going to be added sort of in two parts. This is still our hydrogen, and this is our negative oxygen. What's going to happen in this case is we don't really have a double bond or anything like this. So we actually do have to make room for it. And to make room for it, we're actually going to create water. So if you had to take a guess, I'm going to use this to make water. What other part should I use to make water? That right there, yeah. So those two guys are going to come together and basically make water. And that is what you're going to end up with over here. So what happens when that happens is you could actually draw it exactly the way it is without the OH on it. So we'll just redraw it exactly the way it is. But what now happens is that carbon that's now empty is actually quite positive now, yeah? And that's really good because what thing do I have left? Something that is negative, yeah? So this guy's actually going to go into that spot, and you're going to put on another oxygen carbon group, yeah? So this actually has a name, and this is what is known as just an acetal. And an acetal has two oxygen carbon groups, this guy, and it has a hydrogen, which is that guy. So if you add one alcohol to an aldehyde, you get sort of an intermediate, which is known as a hemiacetal. You can think of the hemi part as there's OH in it. So if you want to think of hemi OH, there should be an OH group. That's what we have going on there. If you add a second alcohol, it will go all the way down and basically do that. What is the overall change if we added two alcohols? We basically added the oxygen carbon part of the alcohol to the oxygen where the oxygen is and the carbon. So we basically just put this part in here and here to get all the way to the end. That's basically what we did there. Any questions on that there? So a ketone, because it's very similar, will do pretty much the identical sort of reaction. So let's just take a look at what happens with the ketone. And like I said, it's pretty much identical. A little bit different because it's missing a certain thing. So I'll just draw a simple ketone as you could get. And once again, if we add an alcohol, and again, it doesn't matter how big the alcohol is or whatever it is. So I'll just add an extra carbon for fun here. And this first part is going to be just like it was with the aldehyde. So the first part we did, right, was to basically make room for it. And again, it's going to add as H plus and OCH2CH3 in this case minus. Again, more positive, more negative. So we're just going to break that bond to make room, and we'll end up with this. And at this point, we can put in our groups just like we did on the aldehyde. We're going to put a hydrogen there, which is this guy. And we're going to put, in this case, OCH2, should have left a little bit more room, CH3 in there. And that is this group here. And again, those are the two parts to the alcohols. As you probably could guess, this also has a name, and this is what is known usually as a hemiketal because it comes from a ketone rather than a hemiacetal that comes from an aldehyde. It has the same sort of components, except it's missing one thing. It has an OH group, hence the hemi part. It has a oxygen carbon group, this one and this one. It is missing one thing that the aldehyde has, which is there is no hydrogen on that carbon. Yeah, because there's no room for it, basically. So this has no hydrogen, unlike the previous one. And just like the previous one, you could stick on another alcohol onto that hemiketal. And it's going to do exactly the same thing as the previous one. I'll try to get a little bit more room here. Squeeze it in. So if we put on one more alcohol, and I'll just make a smaller alcohol here. And if we decide to put this one on, the same thing is going to happen. Again, this is H plus and OCH3 in this case. We are going to make our water. So once again, OH goes off and this guy goes off to make our water just like it did in the previous one. And that's going to leave my guy the exact same. Make a longer bond because I definitely drew this really badly here to run inside around the room. Exaggerated bond. And obviously in that empty space should go the last part that's missing right here. So that empty spot there should have that. Probably not with the giant line there, but we'll just make some room here. And we're going to put that guy on there. So that goes there. This guy ends up over here in the water. So is this guy actually. And this is known as a ketal, which actually has two oxygen carbon groups, this guy, and no hydrogen. Yeah. So if you add one alcohol to a ketone, you'll get sort of that intermediate, which is the hemiketal. If you add two alcohols to it, it'll go all the way to the end, and you'll end up with that ketal, which basically replaces the carbon-oxygen double bond with two oxygen carbon groups that basically come from the alcohol. So that's basically what ends up there. Any questions on that one there? Yeah. It would be, yeah. Other questions? And obviously, normally you want to draw a giant line like that, I imagine as well. All right, that is chapter 12, they say in the books. Take a break. We're going to skip to chapter 14. Don't ask me why in this book. They didn't just do the last of the organic in chapter 13, which would kind of make sense after 12, I imagine. I guess it made sense to somebody, I suppose. So we're going to go 14 first, then we'll go back to carbs, chapter 13 after that. So chapter 14, here's the rest of the organic buffet here of carboxylic acids, esters, amines, and amides. We're going to talk about, again, the rest of everything. So carboxylic acids, we actually just saw a second ago. It has, again, a functional group that looks like this. Again, that is the functional group for a carboxylic acid. Ester, as we will see, has a connection such as this, a carbon-oxygen double bond and an O in there between the carbon. We have an amine, which is actually a nitrogen containing group. So it typically will have something that looks like ammonia. And we have an amide, which is kind of a combo of a carboxylic acid and an amine. So it looks something like this, as we will see as well. So then we're out of organicness, I think, at this point. All right. All right, so we're going to start here, and we're going to go through obviously each of these. We're going to start here with the carboxylic acid. So as we just talked about there, that carboxylic acid has what is referred to as the carboxyl group. The carboxyl group is the functional group of a carboxylic acid. It actually has kind of two groups in it, if you will. We saw our carbonyl group and also our hydroxide group for our alcohol in it in here. In sort of condensed formula, this is oftentimes abbreviated like this, COOH. So if you see COOH, that is COOH. So that's what it looks like basically there. And carboxylic acids, in terms of naming, not too bad. You still go with the longest carbon chain, and you just put oic acid at the end, and you have your carboxylic acid name. So, for example, that is a 1 carbon, and that's based off of methane. This is what is known as methanoic acid. So, oic acid basically is our carboxylic acid. Now, bless you. We also can have, as you can see here, a benzene ring that actually has the carboxylic acid kind of off the ring, if you will. And that is what is known as, like you see there, maybe or not see, benzoic. I can't even see it. Benzoic oic acid. I butchered that very badly there, I think. That is some very bad butchering, I think. Benzoic acid. Just clean that up a little bit there. We'll take care of that in post editing and just get that out of the video. All right. Benzoic acid, which now looks really small again. So there it is. We can also see propanoic acid here to our left. And again, if we just count our carbons, 1 carbon, 2 carbons, 3 carbons. So based off of propane, drop the last part of propane, put oic acid. So you get propanoic acid. The guy in parentheses is the common name. You don't have to worry about the common name. There's probably only a couple that you may have to worry about, but really this one here is probably one you should understand the common name. This is 1 and 2 carbons. This is our carboxylic acid, and that is based off of ethane, so ethanoic acid. Ethanoic acid is also acetic acid, which is definitely commonly used. That's basically your main component of vinegar. Yeah, so you sometimes see that. And this is why sometimes people will write the formula for acetic acid like this. And right there is your carboxylic acid group. So again, that is sometimes how in formulas the carboxylic acid group or carboxyl group is sort of abbreviated. So when you see that, that is, again, what the connection looks like down there. Any questions on that there? So again, basically just going to drop the E and add in oic acid. You do not need to give the location of the carboxyl group, and that is because of the same reason you do not need to give the location in an aldehyde, because at the end of this carboxylic acid group is what? Is a hydrogen. Yeah. So again, it could only be at the end of the molecule. Otherwise, this hydrogen is going to have too many bonds. So much like the aldehyde, because it also has that hydrogen at the end, it will only be at the end. Just like the aldehyde, though, if you needed to number the carbons, because there's other things attached, which one should be carbon number 1? Where that carbon-oxygen double bond is. So that is just like in aldehydes. That should always be carbon number 1 if you need a number for somebody else. So for example, if you had, something like Like, something like this, for example. Why don't you give it a try? What do you think you would call that thing? All right, how many carbons I got? 6 seems like a winner. That is a carbon. Again, there is an oxygen drawn there, so that's not a carbon, right? So that's 1, 2, 3, 4, 5, and 6. You could come down this way, but I think you're only going to get to 5, right? So that's not going to be obviously the longest. So we do have 6 carbons. This right here, right, is our carboxylic acid group, right? Our carboxyl group. And because it has 6 carbons, this is going to be based off of hexane. Going to drop the E and add oic acid. So this is going to be hexanoic acid. Again, we don't need to give the location of where that is, but now we do need to give the location of our group that's attached, and we do need to start numbering here, right? As carbon number 1, that would be carbon number 2, carbon number 3, carbon number 4, carbon number 5, and carbon number 6. That means that carbon number 4, that is where we have our methyl group, right? So in line structure, if it's just a line, nothing attached, that is our friend methyl. So that's going to be a 4-methyl hexanoic acid. Questions on that one there. So as you can see, I would say it's very similar in terms of numbering and naming to an aldehyde, because again, they both kind of have that guy there. And once again, you'll have that group on either side, right? So here, if we take a look, we have our carboxylic acid or carboxyl group there. And that is going to give us 1 carbon, 2 carbons, 3 carbons, and 4 carbons. Once again, you could also get 4 by going up if you wanted to. And obviously, that is where our butanoic acid comes from, based off of butane, which is 4 carbons. Once again, we has to be locked into this guy having the smallest number, which should always be 1 in this case. And we have to number in this direction, which will then lock us in for our methyl group at carbon number 3. And that's going to give us our 3-methyl benzoic acid, our 3-methyl butanoic acid. I jumped the gun looking to my right there really quickly. Now, when we look to the guy to the right, we definitely have a benzene ring happening, right? So that is definitely part of it, but it also has the carboxylic acid group. So that's all one thing. Yeah. So that is the main part here. It is where we get our benzoic acid from, really from benzene, and kind of putting the oic acid at the end of benzene. So it's the same idea. And now because of that, our carboxylic acid is again not really in the ring, but it's attached to the ring. And in terms of numbering, what that means is wherever it's attached to the ring, that carbon in the ring should always be carbon number 1. And remember that the nice thing almost about a benzene is because it has those 3 double bonds, you could go left to right. You don't have to worry about going through a double bond, because you'll always go through a double bond no matter which way you go. So we just want the smallest number for our other guys. And going clockwise, as you can see here with the numbering, should do that. Clearly, if you went counterclockwise, you're going to get larger numbers there for the other groups that are attached. And we also have 2 chlorine groups, which is where the dichloral part comes from. And like normal, we need to give the location, right, where we can find these guys. So that's a 2,3 dichloral benzoic acid. Any questions about there? So here is the IUPAC way of naming, which is the way we're going to name it. Here's some common names. And formic acid sometimes still also pops up. It's still used a lot in everyday life, I guess, in those conversations you have. I don't know why you're having those conversations. And acetic acid is definitely used as well. So again, I would say probably for this, you should probably be familiar with those 2 names, because again, they do tend to pop up along the way. But really, if you had to name either of those, roll with the IUPAC name in here. But again, just keep in mind that they do have some common names that are still kind of used. The other ones, we're not going to use definitely the common names for it, but those two do have a tendency to kind of pop up in places. Formic acid is really methanoic acid, which has the one carbon. And it irritates you if you get stung. And obviously, as I mentioned before, acetic acid, which again is ethanoic acid, again, because of the two carbons, is again the main component there of vinegar, basically. All right. Why don't you give the name for this guy? Why don't you also draw a couple here, if I can make some up, not badly. Let's go with 4-bromo. We'll go not that. We'll actually do camera. All right, let's do 4-bromo hexanoic acid. Let's do 2-ethyl 3-methyl benzoic acid. And why don't you also give me the name for, not that. My organic drawings just died. Let's try that again. And let's do all right, why don't you give the name for that one too? Hope for the best. Could just be drawing squiggly lines, which I might just be doing. One, obviously, this is our carboxylic acid group, and that would then be a carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. Again, your other option would be to go down and then down, and I think you only get to 3, so obviously that's not the longest. So that is 5 carbons with a carboxylic acid. So that is going to give us a pentanoic acid, right? We do have then here one group that's hanging out, which is a methyl group. And because we do need to start numbering here to give this guy obviously the smallest number, that methyl group will end up at carbon number 2 in this case. And that's going to be a 2-methyl pentanoic acid. Any question on that one there? All right, let's take a look at the squiggly lines I drew. Hope for the best here. So let's see. We got 1, 2, 1, 2, 3, 4. We got 1, 2, 3, 4, 5. That to me seems like a winner. Even though it wasn't really what I intended, but we'll go with it there. That's what happens. I can't erase that because that's going to take out the whole molecule there. All right, we'll go with that. Then we're just going to kind of make that out there. All right, we'll go that way. Why not? That is 1, 2, 3, 4, 5. So that is also going to be pentanoic acid. My surprise as well. Yeah, kind of happens when you just draw lines, I suppose. We actually do have a group hanging out here. And we actually should know this group. What group is that? It is an isopropyl group actually, because it does have, I guess it worked out in the end, 1 carbon, 2 carbons, 3 carbons, right? So this guy at the end is CH3, guy in the middle is CH, the guy at the end is CH3. So that is that isopropyl group that we had. That would be at carbon number 1 and 2. So this would be 2 isopropyl. Pentanoic acid, I guess it worked out, I suppose. Good thing I didn't add one more carbon by any chance, yeah. Uh, you cannot, so if you're asking, can you start like here and go up to here? Yeah, so it does have to include the functional group, kind of like, where we have to include the double bond or triple bond. So in that way, we would kind of be avoiding the functional group. So the functional group does have to be part of the longest carbon chain, always. Yeah. Other questions? Okay. All right. Well, let's try the drawing and see how bad that turned out. All right, let's start with this one. Again, we're going to go backwards here. And the first thing I should see when I look at the name is oic acid, which tells me it's a carboxylic acid, right? So then we just want to get our carbons down. Hexane is 6. 1, 2, 3, 4, 5, and 6. Just like normal, because you're drawing it, you could put the carboxylic acid group at either end in this case. It does need to go at the end, right? Because it has the hydrogen. So I'm going to put it actually over here on the right, but you absolutely could have put it on the left. It's perfectly fine. Okay. Now, because I did that, what that forces for me is that is going to be carbon number 1 for me. Now, if you did put it on the other end, your carbon number 1 would be on the left. Yeah. And that leaves us just 4. And we'll go 1, 2, 3, 4. So my 4 should be right about there. And just like everything else we draw at this point, we're just going to fill in the appropriate number of hydrogens. And that's going to give us 3 there, 2 there, 1 there, 2 there, 2 there. And obviously that's not anything, that's just a numbering on that guy. And that obviously would be the condensed formula. You could also, like normal, do the line if you like. You would also start with your 6 carbons, 1, 2, 3, 4, 5, and 6. And actually I need to go down because I got to attach that group there. So that gives me my 6 carbons that I would need. And now we would just go again. This would be carbon 1, 2, 3, and 4 would look something like that. Yeah. Any questions on that one? Obviously, just like the other one, you could have turned it around and put the group on the other end. Any questions on that one? All right, let's take a look at wherever it went here. There it is. We're going to go benzoic acid. So once again, the oic acid part's going to tell me that it's a carboxylic acid. The benzene part is going to tell me that I have a benzene ring. So I got like a little spot for benzene ring right about here. So that is what I'm going to start with. And again, you can, put the lines in. You could do the circle in our class. It's okay. Uh, Remember, though, that the carboxylic acid here is not part of the ring, but it's attached to the ring. And once again, you can actually attach it to any carbon you like. So I'm going to attach it over here to this carbon and just kind of do that deal. And once again, you can attach it to any carbon you want. You could also not do a line structure and actually just put a C there if you like as well, whichever way you want to do it. Because I did attach, though, to that ring there, that will definitely make that carbon for me number 1. And really, because it's a benzene ring, you could go counterclockwise or clockwise in terms of where you put everybody else. So for me, I have at carbon number 3 a methyl group, which would be for me 2, 3 if I went clockwise. And I should have a methyl group there. And if you want, again, you could also put the CH3 and just kind of do more of a condensed type formula. And at carbon number 2, I have an ethyl group, which would be basically a 2 carbon group that will look something like this. And obviously you could draw those groups as lines as well, more line structure-ish if you like. Any question on that one there? All right, so just like normal, we want to just kind of work backwards on the name. Check question? Yes. Yeah, so benzoic acid is basically a carboxylic acid attached to a benzene ring. Yeah. It cannot, it can't kind of incorporate itself into the ring, otherwise it kind of messes up the benzene part of it. So it almost attaches like a group, but because it's actually a functional group, it takes the whole thing as now being one thing. Kind of similar to what we saw with like toluene and like we had those where we kind of take the whole thing. Yeah. 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 Other questions? Yeah. All right. Give a couple names here for these guys. Okay, so let's take a look. Once again, that is your first thing you always want to kind of look for when you have a structure is you want to kind of look for the functional group, right? So that kind of narrows it down to how you should name it and what you should be looking for. So once again, we see our carboxylic acid group there, and that is going to be looking for our carbon chain. So 1, 2, 3. Also, obviously, you could go that way to get 3. So 3 is going to be based off of propane, propanoic acid. Once again, this is going to be carbon number 1. Carbon number 2 is where we're going to find our methyl and a 2-methyl propanoic acid. Any questions on that one there? Once again, I see a benzene ring, but I also see my carboxylic acid, so that automatically kind of gives you a combo deal on that, right? So that whole entire thing is going to be my benzoic acid. Once again, where we attach that carboxylic acid to the ring is number 1. We want smallest number for my other group, which in this case, going clockwise should do that. Obviously, if you went counterclockwise, you would end up with a larger number, and that's going to be 3. And we'll try 3. Then 3-bromyl benzoic acid. Yeah. Any questions on naming, drawing carboxylic acids? Oh, okay. One more for good measure, I suppose. 4-chlorohexanoic acid. Why not? Draw the line structure like it says. Why not? Alrighty, so again, we're going to go this way. The oic acid tells me carboxylic acid. The hexane part tells me 6. Since we're going to draw a line, 1, 2, 3, 4, 5, 6. Remember, you might need an extra one because you don't want to shortchange yourself there because you do have to make the group. Otherwise, obviously, you'll end up with pentanoic acid, right? If you kind of shortchange it there. Um, at that point, that's going to be carbon number 1. That would be 2. That would be 3. And my number 4 would be right there. We do need to draw the Cl at the end. Otherwise, obviously, it's a methyl group at that point. Yeah. Any questions on that one there? All right. All right, let's talk about some properties of carboxylic acid. Carboxylic acids sometimes will make salts that are used as preservatives. And because they are an acid, they will actually go through really an acid-base type reaction. One of the other important features of a carboxylic acid is what we talked about originally here, which is they actually have 2 very polar groups. They have that carbonyl group, which as we talked about is this guy right here. And that again, that oxygen being more negative and the carbon being more positive. And they also have that hydroxyl group or that alcohol group, which is also a polar group. That is really important because it can actually hydrogen bond with itself in multiple locations. So one of the things that can actually beat, for example, an alcohol, as we will see, in terms of boiling points and melting points, is a carboxylic acid. And it's because of these 2 groups, they could actually hydrogen bond, like I said, with each other, and they could hydrogen bond like this, basically. Take 2 carboxylic acids, not drawing the rest of it. And it can actually hydrogen bond, so here. it can do its right there between the negative oxygen here and the positive, and also it could kind of do that hydrogen bonding there. So it could kind of make a dimer. I would drew it a little bit better there, but it can hydrogen bond in two places. And it's one of the few things in terms of boiling point and melting point that could actually beat an alcohol. So alcohol could pretty much beat everybody else that we've talked about. You know, we have our kind of aldehydes, we have our ketones, you know, we had our ethers, right? And then we had really our alkanes, our alkenes, right? And so forth. These guys are on the low end of melting points, boiling points, and freezing points because they cannot hydrogen bond. Alcohols could pretty much beat everybody except for the carboxylic acid because it has these two really polar groups. And because of that, when it bonds with itself, it's going to stay together really tightly, and it's going to take a lot more energy to break them apart to get them like into the gas phase. Is when it happens at the boiling point, and it's going to be a higher boiling point temperature. So as I mentioned, there are also, in addition to having really high boiling points and melting points, they also can hydrogen bond really well with water as well, because they have really those two locations where they can actually hydrogen bond with water. And much like everything else that we've kind of talked about with solubility with water, you can see sort of that almost that magic number of 5 carbons or more, we start to run in again to some trouble with solubility. And again, that has to do with really the non-polar part of the molecule becoming too big and creating what is again referred to as steric hindrance. It basically gets in the way of water being able to interact well with the OH part of the molecule. So less than 5, you're good to go. Definitely soluble. So if you took some acetic acid or some vinegar and water, it's going to mix. But again, once you kind of hit that 5 and above, or really above 5 in this case, you start getting into some trouble in terms of solubility. It's a little bit better because it does have both of those polar groups, but it does start to decrease in terms of its solubility. Because it is an acid, as I mentioned before, it's capable of doing our basic acid-base reactions that we talked about. And in this particular case, this is obviously our acid. This is our acid here. This is our base. And right, it is this hydrogen here that gets donated over to the water that's going to act as a Bronsted base and going to accept the H plus, making our H3O plus. And this is what is known as a carboxylate ion. And if you put like a sodium on that, that is sometimes referred to as a carboxylate salt because it has like a sodium or potassium or something like that. And it basically will do just a regular old kind of Bronsted-Lowry acid-base reaction, donate an H plus, accept an H plus. Actually, this creates our conjugate acid-base pairs, just like we talked about in Bronsted-Lowry. Those two guys again are related to each other.